Let's solve this system of congruences in 2 minutes. We're looking for the smallest value x, equal to 3 modulo 4, 5 modulo 6, and 2 modulo 5. To satisfy the first requirement, we can take 3, or 7, 11, 15, and so on. You can keep increasing by 4, and that obviously doesn't change remainder modulo 4. The next step is to find in this sequence the first value satisfying the next requirement, 5 modulo 6. 3 doesn't work, 7 modulo 6 is 1, not 5, 11 modulo 6 is equal to 5 indeed. So it is solution for first two congruences. Not the only one though. You can increase it by something divisible by all moduli so far, 4 and 6. Least common multiple, LCM, of that is 12, and if you add to something 12, you don't change remainders, modulo 6 and 4, because 12 is divisible by 6 and 4. So all solutions are 11, 23, 35, and so on. Then we look at this sequence of solutions for first two congruences, and we find the first value satisfying the last congruence. 11 modulo 5 is 1, 23 modulo 5 is 3, this is 0 modulo 5. Apparently I need some bigger value. After 35 plus 12, that's 47, and 47 modulo 5 is 2 indeed. So it is the smallest solution for our system of three congruences. Again, not the only one. We can increase it by what? By least common multiple of 4, 6, 5, all moduli values. It's easiest to compute it by taking the previous LCM and the new modulus value and just grabbing those two, computing their LCM. In this case, that's 60. Smallest value divisible by 12 and 5. The smallest solution is 47, but then there's 107, 167, 227, and so on. This method still works if there are more congruences. Let's say that you found solution for first three congruences, x0, and you computed least common multiple of the first three moduli, LCM of this. Then here is the sequence of solutions for first three congruences, and in this sequence we need to find the first value satisfying the fourth congruence. After we find it, let's say it's A, you can keep increasing it by LCM of all four moduli. And now instead of going one by one through them again and computing least common multiple, let's use the fact that we already know LCM of this. Well, we used it here. It was that previous number plus in brackets. And we compute LCM of this and modulus 4. Then the sequence of available solutions is A plus LCM, plus twice LCM, 3 times LCM, and so on. If moduli are coprime, then their LCM is simply the product, like for 5 and 12 it's just 60, but it doesn't work if there is some common divisor. For 4 and 6, their product is 24, and yet there's smaller multiple, 12. If you used product instead of LCM, you would miss some values and maybe also the solution. In the previous example, you would have 11 maybe increased by 24 multiple times. That's a sequence 11, 35, then 50, 59, and so on. And you miss 47, which is solution for first two congruences. And the easiest way to compute this LCM for two not coprime values is to write down multiples of one of the two values, like 4, 8, 12, 16, and so on. Among them, find the first one divisible by the other value. 12 is divisible by 6, so 12. Either that, or alternatively use this formula. LCM is product divided by the greatest common divisor of A and B. The common divisor of 4 and 6 is 2, so LCM is 24 divided by 2. Let's solve this bigger example and learn two new tricks. The first one is that I can reorder congruences to make all the computations easier. When I see equal remainders, it's good to put them at the top, because I immediately see the solution for them. I put third congruence to the second spot, and I know that x equal to 1 works for the first two. Then it can be increased by LCM of 4, 5, those are coprime, so just the product, 20. 20 is divisible by both 4 and 5. 1, 21, 41, and so on. This is a sequence of solutions for the first two congruences. Next step. In this sequence, find the first value satisfying this, so divisible by 3. 1 doesn't work, 21 does work. It is divisible by 3. Here I have 21. LCM of 20 and 3. They are coprime, so simply product. I can increase by 60. 60 is value divisible by all moduli so far, 3, 5, and 4. 21, 81, 141, and so on. And the second trick will be useful because it's a little bit annoying to look at this whole sequence and find the first value satisfying this, 3 modulo 7. 21 is 0 modulo 7, but then every next number gets more and more annoying to compute. So instead of doing all that math, I'm going to do something smarter. 21 modulo 7 is 0, and 60 modulo 7 is what, 49, 56, I think it's 4 modulo 7, which means that basically I'm adding 4 modulo 7. Instead of looking at this number, I can kind of forget about it, and I can say that 0 plus 60 is like 0 plus 4. So here remainder is 4. Then the next one, 4 plus 4 modulo 7 is 1. Then this plus 4 modulo 7 is 5, and so on. This is the second trick. You can just work with remainders to avoid computations with any big values. 5 plus 4, so like 5 plus 60, simplified, is just 5 plus 4, because 4 and 60 is the same, modulo 7. 5 plus 4 is 9, modulo 7 is 2, and I'm looking here for the first value equal to 3. 2 plus 4, 6, 6 plus 4, 10, modulo 7 is 3, alright, done. 0 represented 21, 4 represented 81, 21 plus 60, this is 21 plus twice 60, 3 times 60, 4 times, 5 times, 6 times. This is 21 plus 6 times 60. 360, so in total 381. That's the solution. And if you want to find all the solutions, the new LCM is LCM of 60 and 7. 60 represented LCM of moduli so far, then also we need to consider 7. 60 times 7, 420. Just remember, if they are not coprime, it's not simply a product. So the next solution is 381 plus 420. 801, I think, and so on. That was everything you need to know, but here's something extra. Look at this sequence of remainders. The next element after 3 would be 3 plus 4, so 7, modulo 7, it's 0. Then 4, 1, and so on. This is a cycle. These numbers are then repeated, 0, 4, 1, 5, and so on, and so on. And it means that you don't need to go further because you got all the remainders among first 7 elements. To fit properly the next requirement, modulo 7, you will check at most 7 values. You will not go forever. Actually, if you try to go for more than 7 steps and you didn't find it already, the solution, then either you made a mistake or there is no solution to this system of congruences. If you are a programmer rather than a mathematician, what's important for you is that you need M4 steps, modulus 4, here 7, to fit remainder modulo this modulus. And like, yeah, for the first phase to match the first 2 congruences, you need that many steps, then M3, M4. So that's the complexity for 4 moduli. And in the description, I will link my code for Advent of Code Day 13 problem, because it required Chinese remainder theorem. Thanks for watching, bye.